let's work through some examples together here on the first law of thermodynamics, and we have some conceptual questions that we're going to start with, and then we'll do some numerical problems. So let's read through this first one here together. So we're going to ignore friction and assume that air behaves as an ideal gas. Perfect. So the plunger of a bicycle tire pump is pushed down rapidly with the end of the pump sealed so that no air escapes. And there's little time for heat to flow through the cylinder wall. Explain why the cylinder of the pump becomes warm to the touch. Okay, so there's some information here that we need to pay careful attention to. Little time for heat to flow through the cylinder wall. Essentially, what this is saying is there is no heat flowing into or out of our system. This is talking about an adiabatic process, which means that Q is equal to 0. Okay, what else are we told? We're told that this is pushed down rapidly. It means that this gas is compressed. Which means that the work is done on the gas. Right? The displacement and the force are in the same direction. Volume is decreasing, so work is done on the gas, which we say is positive work being done. Okay, let's work those two things out. Here, the change in internal energy of our gas is equal to the heat added to the gas plus the work done on the gas. If there is no heat added to the gas because it's an adiabatic process, then the change in internal energy is equal to the work done on the gas. And if work is done on the gas, and there is no heat transferred to or from the system, the internal energy or we could say the temperature, right? Remember, the temperature is directly related to the internal energy. Temperature of the gas will increase. Right? Temperature will increase. All right, our next example. A material undergoes an isochoric process that is also adiabatic. Isochoric and adiabatic. Okay, we'll break those down once we finish reading the question. Is the internal energy of the material at the end of the process greater than, less than, or the same as it was at the start? So we want to figure out the internal energy. Is it an increase, decrease? Is it constant? So first, what do we mean by isochoric? Isochoric means constant volume, and adiabatic means no heat transferred. Okay, let's, I think what might be helpful for us is a PV diagram. So for PV diagram, an isochoric process looks like this. It's a vertical line. It means that we have constant volume, we're at a certain volume, and that volume is going to be the same. This can also be an adiabatic process. The examples that we had seen, or the graphs that we had seen of adiabatic processes were curved, but it just meant that they couldn't be isothermal. They couldn't maintain a constant temperature. Here is an isotherm. And we can see that our isochoric process is definitely not an isothermal process. It's not curved necessarily. How we would have both an isochoric and an adiabatic process, what that would actually look like, maybe I'm not quite sure, but if we have it, we can say that this isochoric process is adiabatic. as long as, and that is just to help us say that there is no heat transferred to or from this system. Okay, so I'm just going to erase this isotherm here. Okay, so there is our isochoric adiabatic process. It's a vertical line, which means that the area is equal to 0. In other words, there is no work done on this system. There's no, well, we know that the volume is not increasing or decreasing, so there is no work done. So the change in internal energy, being the heat added to the system plus the work done on the system, if both of these are 0, it means that there is no change in the internal energy. Okay, let's look at this next example. So what we have here is a pressure volume graph, a PV graph, in which a gas expands at constant pressure from A to B. So over here, constant pressure from A to B, and then it goes from B to C at constant volume. And what we want to do is we want to fill in this table below to determine the sign of the change in the internal energy, the sign of the heat, whether it's heat transferred to the system or removed from the system, and then the sign on the work, whether it's work done on the system or work done by the system. And we want to justify why we have chosen each sign. So let's start with A to B. And we're told that the change in internal energy is positive in this process. We're already told that, so that might help us in determining some signs. So first, let's look at our graph. And what can we see from the graph? Well, we can look here at the area. This is an isobaric process. The area here is going to tell us the work done on the gas or by the gas, depending on whether we have an increase in volume or a decrease in volume. So in this case, the change in volume is positive, right? We have an increase in the volume, and so that means that the work is negative. This is work done by the gas. So let's put a negative sign there. Now, how do we know about the heat? We didn't really have anything in our notes about what the sign on the heat is for an isobaric process, but what we're told is that the change in internal energy of this gas is positive. And so, if the work is negative, and the change in internal energy is going to be positive, and the change in internal energy is simply the work plus the heat, then Q must be positive, right? It must be positive and it must be greater than the work for us to end up with an increase in internal energy. So that's what we can say. That means that heat has to be added to this gas. Okay, and then let's look at process BC. If we're going to go from B to C, well, the work is 0. Why is the work 0? Well, there's no area under that graph. This is an isovolumetric, isochoric process, which means that the volume remains constant. There's no work done. And then, right, so let's write that down. The volume is constant. And so if we have no work done, we have heat added to the system as indicated already, then that means that there's going to be an increase in internal energy because Q is positive. Okay, and our last conceptual example. Suppose you want to heat a gas so that its temperature will be as high as possible. Would you heat it under conditions of constant pressure, isobaric, or constant volume, isochoric, and why? So let's see. Let's start with some PV graphs. PV graphs are going to help us solve a lot of these problems, really see what's going on. So let's start with our isobaric process, constant pressure process. And we're trying to increase the temperature, so that means we're going to be going this way, right? We're going to be going to the right. And so if we are doing that, well, first thing we can notice is that there is some work that is done by the gas. Why do I say it's done by the gas? Well, the volume is increasing. So this is negative work. So that means that if we are increasing the temperature, if we are adding energy to this system, the gas is actually going to be doing some work, which means that some of the energy, it basically means exactly that. Some of the energy that we're adding to this system is used to do work. Right? Delta U is equal to Q plus W. Whatever amount of heat we're adding to the system, well, some work is being done that's negative work, so our increase in internal energy will not be fully equal to that addition of heat. Whereas if we have an isochoric process, constant volume, that looks like this. An increase in temperature for an isochoric process starts low and ends high. This has no work done. The volume is constant. So all of the energy, maybe we're to increase the temperature here, we're increasing the heat, we're adding heat. All of the energy is going to be used to increase the internal energy and thereby the temperature. So if we're going to add a certain amount of energy into the system, we would rather have an isochoric process or a constant volume to maximize the temperature, to have the highest temperature possible. Okay, let's look at some numerical problems. So we have a system that does 164 joules of work on its environment, and it gains 77 joules of heat in the process. So we want to find the change in the internal energy of the system and then the environment. So let's first write down what we know. We're told that the work, 164 joules, the system does the work on the environment. It's done on its environment. And so that means that this is negative work. This is work done by the system, negative 164 joules, right? Work done by the system. But it also tells us that the system gains 77 joules of heat. This is heat added to the system. Okay, so the change in internal energy of the system, Q plus W, we have positive heat added to the system, we have negative work done by the system, and this works out to be negative 87 joules. So what that tells us is there's 87 joules lost by the system. There's a decrease of internal energy of 87 joules. Where does that energy go? Well, if 87 joules are lost by the system, that means that 87 joules are gained by the environment. All right, let's look at this. In moving out of a dormitory at the end of a semester, a student does 1.6 times 10 to the 4 joules of work. In the process, his internal energy decreases by 4.2 times 10 to the 4 joules. Determine each of the following quantities, including the algebraic signs. Let's find the work, the change in internal energy, and the heat. So, first, the work, well, let's think about this. It says that the student does work. So the work is done by the student. So this gives us the sign. It means that the work is negative. and we're told that quantity, 1.6 times 10 to the 4, so work is equal to negative 1.6 times 10 to the 4 joules. Okay, internal energy, we're told that his internal energy decreases. Okay, this one's easy, decreases, so it's negative 4.2 times 10 to the 4 joules. Right, this is a decrease. To figure out the heat transferred to or from the student, so equals change in internal energy is equal to Q plus W, so the heat is equal to the change in internal energy minus the work. And let's plug in what we know. Change in internal energy, negative 4.2 times 10 to the 4 minus negative 1.6 times 10 to the 4, and we get that heat is negative 2.6 times 10 to the 4. What does that negative sign mean? That means that this is heat lost by the student or transferred from the student. Okay, 2 more examples here. So a gas, while expanding under isobaric conditions, does 480 joules of work. So it does work. The pressure of the gas is 1.6 times 10 to the 5 pascals, and its initial volume is 1.5 times 10 to the negative 3 meters cubed. And we want to know what the final volume of the gas is. So let's write down what we know first here. Work done by the gas. So it's negative 480 joules of work. The pressure, it is an isobaric process. That means that pressure is constant. So we're not going to have an initial pressure and a final pressure. We're just going to have a constant pressure, which we're told is 1.6 times 10 to the 5 pascals. We have an initial volume of 1.5 times 10 to the negative 3 meters cubed, and we want to figure out what the final volume is. So if you wanted to, you could draw a quick little PV diagram. It's going to look like this. And we need to think, are we going from left to right? Are we going from right to left? Well, if it does say that it is expanding, so that means we are going from, here's our initial position, here is our final position, and we know that the work is simply going to be the area under here, or the work is negative P delta V. So the graph helps us visualize, but we're going to end up with this equation here to help us solve this. So let's figure out what the change in volume is. First, we know what it's equal to the negative of the work divided by the pressure. So negative 480, there's 2 negative signs here, divided by the pressure 1.6 times 10 to the 5. We end up with a change in volume of positive 3 times 10 to the negative 3 meters cubed. That means that our change in volume, simply our final minus our initial, tells us that our final volume is going to be our initial volume plus the change in the volume. That makes a lot of sense. And if we had an initial volume of 1.5 times 10 to the negative 3 meters cubed, and we increase that by 3 times 10 to the negative 3 meters cubed, then that means we have a final volume of 4.5 times 10 to the negative 3 meters cubed. Okay, let's work out our last example here. So, the pressure and volume of a gas are changed along this path. We're going to go from A to B, from B to C, and then from C back to A. We're going to do a full loop here. And using data in the graph, we want to determine the work done in each of the following segments. So, let's go from A to B. From A to B, well, this is an isochoric process. It's a vertical line, and if we look on the graph, we are maintaining a volume of 2 times 10 to the negative 3 meters cubed. If volume is constant, that means that work is equal to 0. There's no work being done. There's no area under a vertical line. Okay, let's go from B to C. B to C is a isobaric process. We are maintaining constant pressure. For an isobaric process, the work is equal to the area under that graph, or negative P delta V. When we have an increase in volume, this should be work done by the gas. It should be negative work, which we will end up with. So negative, the pressure is 7 times 10 to the 5 pascals. The change in volume is the final volume, 5 times 10 to the negative 3, minus the initial volume, 2 times 10 to the negative 3. And we end up with work being negative 2100 joules. Negative meaning work done by the gas. And then from C back to A. Now, what kind of process is this? It's not isochoric because it doesn't have constant volume. It's not isobaric. It's not isothermal because it's not that nice curve that goes from up and left, down and right. So this, well, it's maybe not any one of those processes, but it's something we can still analyze if we're only trying to figure out the work, because work is simply the area under the graph. And here's the area under the graph. All of this stuff, which is simply a triangle plus a rectangle. So if we can figure out the area of that triangle, figure out the area of the rectangle, then we can determine the work done. And we need to also think about the sign. So our triangle, how do we find the area of a triangle? 1/2 base times height. So in this case, 1/2 times, so the base, 5 times 10 to the negative 3 minus 2 times 10 to the negative 3 is the width of that base. The height of that triangle, it goes up to 7 times 10 to the 5, up from 3 times 10 to the 5. And this triangle gives us 600 joules. Our rectangle, length times width, length is 5 times 10 to the negative 3 minus 2 times 10 to the negative 3, and our height is 3 times 10 to the 5. This is 900 joules. So our work then is equal to our triangle plus our rectangle. It's 1500 joules of work. Is it positive or negative? Well, we have a decrease in volume, which means that work is being done on the gas, which means it's positive work. So that means it's positive 1500 joules. Notice that to go from A to B to C back to A, look at all the work that's done. We did 0 work to go from A to B. We did the gas did 2100 joules of work to go from B to C, but then we did, or something did, 1500 joules of work to go back to A. The net work is not 0. So in that case, that means that either heat was added to the system or removed from the system, or there was some change in internal energy. We don't know those details about whether the temperature increased or decreased or whatnot. Actually, we do know that the temperature ended up back being the same, right? Because we're back at location A, back at the same position on the graph. We're not higher up on the graph or further to the right on the graph. We're at the same position. So that means that that difference in the works must be the heat added to or removed from the system. Okay, that's it for these examples. And that's it for the first law of thermodynamics.